So we want to get into starting to predict some of the group behavior we see in the table and the periodic trends. And we're going to talk primarily about size trends and metallic character briefly, but then trends about giving or taking away electrons from either an atom or an ion itself. In order to understand these trends, though, we have to understand why these trends exist. And this comes back to shielding. Shielding, which is also known as your screening effect, is the reduction in the nuclear charge that's experienced by an electron due to the presence of other electrons. What does this really mean, though? Well, in Chapter 2, we defined the number of protons in an atom to be equal to the number, or the letter Z. So Z is, number of protons here. But we have what we call Z actual. So we see our effective nuclear charge here. Z actual is the actual number of protons that atom has. So atom or ion, whatever that species has in the number of protons, that is your actual value of Z. But from that, we subtract this value of S. S represents our shielding effects, and we get what we call Z effective. Z effective is really how powerful is that charge of the protons in the nucleus. So think about what we've got here. In our nucleus, we've got your protons and your neutrons. Neutrons aren't going to do anything. They don't have any charge to them. They're just neutral species that just add mass to your atom. But the protons have a positive charge. The electrons are floating outside of here, and electrons have a negative charge. So we've got, your protons, we've got your electrons, and we know based on Coulomb's law, these are attracted to each other. Plus, opposites attract. But we talked about Coulomb's law in another chapter and saw that, Coulomb's law really looks at the distance between the species themselves and then their charge to each other and how attracted are they to one another. So these electrons are attracted to your nucleus. The trick to this, though, is that some of these electrons are being blocked by other electrons. So what we see here is what we call your outer electrons versus your inner or core electrons. Everything's attracted to your nucleus. But we also know that these electrons, these inner electrons and outer electrons, are repelling one another. They have the same charge, and they don't want to be around each other. So effectively, what happens is these electrons that are closer to your nucleus block the full power of those protons from your outer electrons. It's kind of like, say that you go to a concert. You go to the concert here at TCU, and you've got the stage. If you're one of the people up here, you're seeing the person better than the people back here. And you guys are scattered with rows of people. The closer you are to the stage, the better you see the people on the stage. The electrons are the same thing, except instead of seeing, it's the pull of that positive charge from the nucleus. These electrons up front are going to feel the pull stronger because they're stronger. These electrons are going to get a weaker pull because all of these electrons in front of them are already pulling stronger than they are. So the farther we get away from that nucleus, the less they feel the pull of that nucleus. So that's why we call it your Z effective. What the electron feels out here is weaker than what the electron feels up here because of how far it is away from this nucleus. So to predict periodic trends, we need to consider two different things. We need to think about your electron configuration and your nuclear charge. And so what I mean by that is your Z actual or Z effective, the number of protons you have. So Z effective is what it's actually feeling, but we do want to consider the actual number of protons because then we can think about where these reside, where is the electrons residing, and how much is it actually pulling towards itself. Effective nuclear charge. So again, electrons are simultaneously attracted to the nucleus, but also repelled by one another. These outer electrons, so the farther we are out of the field, are shielded from the full strength of the nucleus. We call this your shielding effect. The effective nuclear charge, just that net positive charge is attracted to the electron. So effective nuclear charge, how much is this electron actually feeling this pull because this guy's out of the way, pulling some of it away. The valence electrons. Valence electrons are the electrons that are the farthest out from your nucleus. So for lithium, this is our valence electron. Your valence electron feels less than the full positive charge from the protons in the nucleus. It only feels your effective nuclear charge. That effective nuclear charge is dependent upon the position of the electron. If we had a different element than lithium that had farther shells out, an electron out here would feel a different pull than an electron here. Electrons in the same valence shell, though, shield each other very little. Most of the shielding comes from the inner core electrons. So that means that this electron and this electron, which are both in the 1s shell, don't really shield each other very much, so we pretty much ignore that effect. It's really their shielding to other electrons outside of their shells. And our periodic trends. We will cover each one of these individually, but just as a general summary slide for these and what we're going to talk about in the other videos. Atomic size increases as we go down the table and from right to left. Ionization energy. Ionization energy is the amount of energy it takes to remove an electron from something and making it a positive or cation, giving it a positive charge. And so ionization energy tends to increase across the table and up the table. There are exceptions. Electron affinity is how much does it want the electron, and that tends to increase across and up the table as well. But there are tons of exceptions to electron affinity, and we will cover those. Electron affinity is truthfully easiest just to predict if you look at the configuration itself. It's easier to think about the atoms themselves and think about what it would actually take. Ionization energy, the trends work for the most part. There's some major exceptions though, but if you think about electron configuration, it makes sense. And atomic size follows this pattern along with ionic size for the most part. And we will cover those in just a